G'day chemistry students. In this video we're going to be looking at inter and intramolecular bonding. That covers dot point 1.4.5 and let's get into it. So first off, let's distinguish between intra and intermolecular bonding. So first off, intra means within and inter means between. So we've actually already looked at intramolecular bonding in the last couple of videos. So they are the bonds that exist within molecules themselves. So ionic bonds, covalent bonds, metallic bonds are all examples of intramolecular bonding. Now what we're going to be expanding on today is our intermolecular bonds. So bonds that exist between our molecules, which essentially hold them together and may even have an impact on the state of matter of the substance. I really like what Khan Academy has done, the analogy that they've sort of put into picture here. Essentially, if I have a hydrogen and a chlorine atom, I can form a molecule or an intramolecular bond by threading them together and stitching them together. And those bonds are quite strong and very, very, very difficult to break. Whereas if I was to put all of these molecules that I've made that all have intramolecular bonds together, if I was to put them together with some Velcro, this would be analogous or similar to the concept of our intermolecular bond. So the bonds that exist between each of the separate molecules that hold them together a little bit more closer. Now, as soon as we put any force, the thing that's going to break first are those intermolecular bonds rather than the bonds between the individual atoms. Now, there are three kinds of intermolecular forces that we're going to be looking at that hold atoms together. Their strengths are all different, and I'm just going to break these down and we'll look at them a little bit more in class. Now, the first one is a dipole-dipole attraction. And these attractions have a lot to do with the electronegativity of the atom. Also, take note that these forces that I'm talking about occur in covalent molecules. I should have said that before, apologies. And what we end up having is, say, chlorine and hydrogen, which have fairly different electronegativities. Chlorine is actually much better at drawing in electrons than hydrogen is. So even though the atoms are sharing their electrons, what ends up happening is that the chlorine sort of dominates and has the electrons on its side more than the hydrogen usually would. And I'm going to draw that up really quickly. So if I have my hydrogen and chlorine and they're bonded together, most of the time the electrons are going to be sitting closer towards the chlorine. Now, that doesn't mean that the hydrogen has given away its electrons. It's not an ionic bond. But what it means is that most of the time the chlorine is a little bit more negative than neutral and the hydrogen is a little bit more positive than neutral, but not to the same extent that ions are, a positive or a negative ion. And so we use this delta symbol to say that we have a partial charge. So the chlorine has a partial negative charge and the hydrogen has a partial positive charge. And what can happen is that those partial negative and partial positive charges can attract to each other, and the partial positive and the partial negative can attract to each other as well, and this attraction can happen over and over and over again, forming what we call a dipole. Two different poles, or the poles being the positive and the negative charges. We can also describe these bonds as polar. Now there's one other polar bond that I'm about to look at, but these polar bonds mean that there can be an attractive force consistently with a positive and a negative charge on two different parts of two different molecules. Now, there are also these things called hydrogen bonds. Now, they only exist for nitrogen, hydrogen, oxygen, hydrogen, and fluorine hydrogen. So our most electronegative atoms end hydrogen. And these hydrogen bonds are essentially dipoles as well, but they're a little bit stronger than our average dipole bond. Oh, sorry, a dipole intermolecular force. So they get their own special name. They're identified in this way because they're a little bit stronger, and that will have application in future modules. We'll get to that when we get to that. But yeah, the main idea is there are other dipoles called hydrogen bonds. In the example for water, there are oxygen-hydrogen bonds forming positive dipoles on one side, or positive poles on one side, and negative poles around the oxygen, and they can also attract to each other as well. Now, what can happen is that not all intermolecular forces are polar, some of them are non-polar, where the difference between the electronegativity of the two atoms is minimal or zero in the case of bonds formed between the same atom. So examples would be two atoms that are the same that are bonded together. Others might be something like carbon and nitrogen, or carbon and hydrogen in particular as well. Again, they will come up in later modules as well. Now, what we have here are what we call London dispersion forces. You may also hear the term van der Waals force, and they're caused by what we name as dipole moments. Now, this diagram is a little bit complicated, but essentially, and I'm going to look at this example first because it's for a molecule, not just an atom. But what can happen is, and we're just going to leave this to an explanation of random chance, but there are random chances that a molecule which is usually has no charge because there's no pull from any electronegative atoms in either direction, but a bond that usually would have no charge can end up spontaneously having a charge on either side. And this is because electrons don't exist in a fixed place. At any one point in time, electrons could be sitting on one side or the other. So my example here is if I have a hydrogen bonded to a hydrogen, usually the electrons will be dispersed fairly evenly between the two molecules. But there can be times where, similar to the dipole, there can be two electrons sitting on one side of the hydrogen and no electrons sitting on the other. Now we call this a dipole moment because there is a dipole for a moment in time. What that could mean is that these hydrogens could have a moment where they are attracted to another molecule undergoing a dipole moment. Or what could end up happening as well is that there might be an inducement of, or an inducing of, a dipole in a molecule that's near it. So as an example here, we had this dipole moment where we had a partial negative and a partial positive charge. But because there was a partial positive charge over here, the molecule that was next to it ended up getting a partial negative charge because the electrons on this bond were attracted towards the partial positive that was very close to it. Now, this can happen as well. There can be both sort of instances where it may just happen to be attracted to a molecule that's near it that's already got a partial charge, or it may induce a partial charge as well. Now, we don't have to know any of these concepts in massive detail. They will come up in context, especially in the HSE course. I'm looking at Module 7 in particular when I'm saying this. So we will revisit this concept as it needs to happen, but it's something that we're sort of introducing now for the first time. Now that concludes today's video. In the next one, what we're going to be doing is looking at some practical skills. Now we've already begun to do some gravimetric techniques in the class, but this video will explicitly sort of explore some of those techniques and how to actually do them. Until the next one, catch ya.